This is the second of 3 demonstrations designed to help students understand the tri-stimulus theory of color perception. While this theory forms the basis of color reproduction technology in photography, film, television, and printing, it is by no means the complete story of how color perception works. However, I will use the theory to explain how the mixing of pigments, dyes, inks, and paints is used to achieve different colors. When we considered additive color, we thought about mixing the different colors of light. We added the colors together. In order to understand the distinction between additive and subtractive color, it is important to remain focused on light. Though we are adding paint colors to each other, we are increasing the paint's ability to absorb light, and the new color is achieved by subtracting some light. In the additive demo, I started with a dark screen onto which I projected colored light. In mixing colored pigments, I begin with a white screen that represents white paper onto which I shall apply different subtractive primary pigments. The 3 primary pigment colors, or primary subtractive colors, are yellow, magenta, and cyan. The yellow pigment absorbs blue light, allows red and green light to pass through or reflect from its surface. We perceive the red and green light and see yellow. The magenta pigment absorbs green light, allows red and blue light to pass through or reflect from its surface. We perceive the red and blue light and see magenta. The cyan pigment absorbs red light, allows green and blue light to pass through or reflect from its surface. We perceive green and blue light and see cyan. Yellow ink absorbs the blue light. Cyan ink absorbs the red light. Thus only green light remains. Green is a subtractive secondary color achieved by mixing 2 primaries. Yellow ink absorbs the blue light. Magenta ink absorbs the green light. Only the red light remains. Red is a subtractive secondary color achieved by mixing 2 primaries. The magenta ink absorbs green light. Cyan ink absorbs red light. Only the blue light remains. Blue is a subtractive secondary color achieved by mixing 2 primaries. When all 3 of the primary subtractive colors are in the mix, primary yellow absorbs, i.e. subtracts the blue light, primary magenta subtracts the green light, and primary cyan subtracts the red light. With all the light absorbed, we see black. White light minus red light minus green light minus blue light is no light. Notice that the secondary colors derived from mixing any 2 of the primary subtractive colors are the same as the additive primary colors. Red, blue, and green are additive primary colors. Red, blue, and green are secondary subtractive colors. Yellow, magenta, and cyan are primary subtractive colors. Magenta, yellow, and cyan are secondary additive colors. That is the theory. In reality, when we mix the 3 primary subtractive colors to get black, we actually get something that's not quite black. So the printing industry uses a CMYK color space. K is black ink added to the 3 primaries to compensate for the inadequacy of the primary inks. Now we will do the same experiment we did with the additive after images. Using the subtractive colors, fix your eyes on the white dot in the middle of the black space for 30 seconds. Starting now, I will let you know when the time is up. Stay focused on the white dot until the screen turns white. 20 seconds. You are seeing the complementary colors, complementary to the ones you've just been looking at.